What would happen in this scenario? Go ahead and predict the products of this reaction. So in this case, we're going to get a hydroxyl group on the more substituted position of the alkene. So let's go over the mechanism for this. The H3O plus is an hydronium ion. It's generally going to be an acidic solution. A lot of times the way we generate these hydronium ions is by having sulfuric acid in the solution. The pi bonds electrons are going to attack one of the hydrogens, and then the hydrogen would be going on one of the carbons across the double bond. Now, you could either go, if you imagine this hydrogen as red, it could either go here, or it could go here. If it goes up here, then the positive charge would be formed on the secondary carbon. If it goes down here, it's going to be on the primary carbon. Carbocations that are secondary like this are more stable than the primary ones, so this would not occur as often as the top situation. We also have water molecules in the solution, and so this water can act as a weak nucleophile and attack the carbocation. So we would end with a situation like this. And then another water molecule can act as a weak base. Take away one of these hydrogens, and we would get the alcohol group on the secondary carbon. Now imagine that we have another molecule that looks similar to the last one, but that there is a methyl on a carbon next to it, and let's say there are two methyls on a carbon next to it, and we react them with the same thing. What would be the outcome in both cases? So in this top scenario, we're going to have and then in the bottom we will have now this might seem confusing, so let's explain the mechanism for both. In the top scenario, we have the hydronium ion, which this is basically this rewritten as a bit differently so that we can take away the hydrogen. These pi electrons will attack the hydrogen, and then we will get an intermediate that looks like this. You should recognize that here this hydrogen atom can move as a hydride. So that now the positive charge is on this tertiary carbon. And now water will attack as a weak base. it really is a weak nucleophile, and now it'll be a weak base. In this scenario, what will happen is a little different. We will still have the hydronium ion, and then the electrons will attack the hydrogen from it. But in this case, there's no hydrogen on this carbon that can shift. There's no hydride shift that can occur. But what we can do is a methyl shift, where the entire methyl group leaves and enters and goes to this carbon atom. So that will leave a positive charge on this carbon and get rid of it on this one. We can then attack with water. It's not very clear what happened here. In order to get this molecule to form this, we just need to use water as a weak base and get rid of this hydrogen. And that will give us this product. Go ahead and predict the products of this reaction. So this reaction, we would have the major product being don't have space to draw it, so let's move everything. Now let's explore how this occurs. This is very similar to what we've gone over, except instead of water as being the solvent, we have ethanol as the solvent. We're going to have certain ions in the solution which are going to look similar to hydronium, but in this case they're actually going to have two hydrogens and an ethyl group on them. And this is going to be a positively charged oxygen. So the pi bond electrons again attack a hydrogen. And this gives us the hydrogen again. Imagine it being red. Could have drawn that better. We go on the secondary carbon cation on the tertiary carbon. At this point, the solvent molecules, which are ethanol, this has electrons, so it can be a weak nucleophile attacking the carbocation. But notice that there's a hydrogen still on this, so this would be a positively charged molecule. And we can use another ethanol molecule to deprotonate it. And we get the product.